guys a rather quick overview of differential equations, show you the main calculational ideas. To start with, I'm just going to talk about some terminology. So what is a differential equation? I mean, a differential equation, in short, is an equation that involves derivatives. I mean, give or take, that's really it. So there's some typical things notation mean, right? dy dx could be y prime. It could be, y prime could be dy dt. Sometimes we use x as the independent variable. Sometimes we'll use t as the independent variable. Over here, I'm using x and y as dependent variables, but I'm using t as an independent variable. So the larger point here is the notation in this course is not exact for saying x could be a dependent or an independent variable, depending on context. So the next thing to talk about is what's the order of a differential equation. That's not terribly complicated. Basically, it's simply with the order of the differential equation, whatever term you have in the differential equation which presents a derivative of the highest order in a non-trivial fashion, that defines the order. So like here, I have a second derivative, which makes a second order. Here I have a kth derivative, that makes a kth order. You can talk about whether the differential equation is linear or not, all right? This is not linear. This is not linear. This is not linear. This is linear. The reason this is linear is because the r is the dependent variable and it appears linearly. The fact that theta is not a constant doesn't matter, but the fact that we've got a y squared here, which is the square of the dependent variable, that makes it nonlinear. The theory for solving linear versus nonlinear differential equations is really different. As in, there is a theory for linear equations, and there's not as much for nonlinear. Except in the first order case, in which case we can say lots of things. Now, one of the problems we're going to be solving today is the nth order linear ODE in standard form. In fact, if everything goes as planned, I'll show you the complete and unflinching solution to this problem. A to the n, an minus 1, yn minus 1, a0 times y equals to g. G is called a forcing function, and well, we're going to solve it for the case that the coefficients are constants. All right, maybe tomorrow or whenever we meet again, we'll look at one of the constants or functions that requires something sneakier. You can either talk about a single differential equation like what I was talking about, or you can also talk about solving a system of differential equations, just like we can solve a system of linear equations in linear algebra, right? So here's a system of second order ordinary differential equations. Now, beyond that, of course, so most of this course is about ODEs, but then a lot of times in physics you face things called partial differential equations. A partial differential equation is a differential equation which is based on more than one independent variable. You actually have several independent variables, like you could have y and x. This could be like the temperature, and this is how the the temperature changes with respect to y and x at a point. Or here's the Laplacian of a potential energy function in 3 dimensions. Or here's the divergence of an electric field, or the curl of a magnetic field. All of these are involving partial derivatives of one or more with respect to one or more independent variables. In this case, you could think about one dependent variable, one dependent variable, one dependent variable. Here, actually, there would be three dependent variables: the x, y, and z components of the electric field, x, y, and z components of the magnetic field. These kinds of partial differential equations are the ones that appear in second semester physics and study of electromagnetism. Although I don't think this course really does justice to the techniques you need to solve those kinds of equations. Those are, well, some special cases, I guess we'll get to. But so anyway, that's a PDE is a partial differential equation, and ODE is an ordinary differential equation. Okay. So what's this course about? I mean, what's the philosophy? What's our game plan? Basically, is to solve ordinary differential equations and partial differential equations in as much as we can. Most of our focus, again, on ODEs. So what the first order of business is to ask is what is a solution to a differential equation? Well, you can talk about a specific solution, or you can talk about having the general solution, right? So a general solution is some kind of family of solutions which covers all possible contingencies, let's say, whereas a specific solution is, well, just an ordinary solution, right? So to give an example, if you had this differential equation, y prime prime plus y equals to 0, I could say a specific solution would be something like y1 equals to, say, sine of x, right? And I could give another specific solution. I could say y2 is equal to cosine of x. Now, the reason that these are solutions is you can easily check that if you differentiate those functions twice, you get minus the sine again or minus the cosine again. So when you add y prime plus y, you get 0. So when you plug them in, they work. That makes these solutions. Now, the general solution, it turns out, for reasons as we'll discuss as we go on, for this differential equation, something like this, c1 cosine x plus c2 sine x. So that will be, these are, let's say token solutions or specific solutions. This is the so-called general solution, which is, technically speaking, it's actually a family of solutions. So you've seen this sort of thing before when we talked about integration, right? When we talked about integration, we also had this kind of problem. A very similar situation. We said something like, okay, so if I've got, x, if I've got x equals f of x, then if I have big F of x equals x squared over 2, this is an example of an antiderivative, right? Because if I differentiate big F, I get back little f, right? But what did you guys do? If you wrote that on the test, a lot of times you lost points, right? We wanted you to write the integral of x dx is equal to x squared over 2 plus a constant, right? And to be totally honest with you, that isn't even an abuse. In some sense, that's an abuse of notation as well, because the more proper thing to work with would be classes of functions. So, I would really rather say that the indefinite integral is in fact a set of functions. There's a formula, x squared plus 2 plus a constant such that c is a real number. So, in some sense, the general solution being that, I guess I don't really like that. I would like to say there's a general solution set, and the solution set is something like this. So as you can see from a perspective of linear algebra, this is a two-dimensional solution set, whereas our indefinite integrals have a one-dimensional solution set, where the constant is the coordinate. Okay, so anyway, we want to understand, you already understand how to do this, of course, but we want to understand how to, I pulled these from the thin air, right? I didn't explain how to get this, how to anticipate it, how to understand it yet. I'm showing you an example of what a solution is. Now, the other thing to think about with solutions is we also have solutions which, so that would be an example of an explicit solution. We also have what are called implicit solutions. So the notion of an implicit solution, for example, would be something like this. Maybe I have x squared plus y cubed equals to a constant, right? 10. Well, this would implicitly define y as a function of x, right? So if you want to see a differential equation, which has this kind of function appear as a solution, what we do is, well, I can differentiate it to figure, I'm kind of working backwards here. So differential is what, 2x dx plus 3y squared dy equals to 0. So you see dy dx equals to minus 2x over 3y squared. This differential equation has this as an implicit solution. Now I showed you the man behind the curtain here. The more interesting question is, when can I start with this and get back to that? And is that generally possible? We'll be talking about that shortly. Anyway, so I would just say, I don't want to handicap myself in some sense and say the only thing a solution can be is a function. I think that's too limiting. I would also like to allow myself to say solutions could be equations, could be given by equations, at least for this course. So we can either talk about an explicit or an implicit solution. Now that's again an example of a specific solution, but you could also talk about like a general implicit solution if you wanted to. We don't need to do that. So my next point to you is differential equations is nothing new. We've already been solving differential equations in calculus 2, right? So if you think about it, whenever you solve something like, oh man, that's not what I want to say here. here I'm showing you how we could solve certain differential equations just by integrating, right? For example, if I wanted to solve dy dx equal to 0, I integrate both sides, I get y as a constant. If I want to solve y prime prime equal to 0, I just integrate twice, I get a linear solution, right? Or a defined linear. Y equals c1 x plus c naught. But you know, you can't do that to these examples I just erased over here, the y prime prime. Oh, that's right. Get somebody's doing some sightseeing up there.
What?
Somebody's walking on the roof.
Oh.
Can't fix this problem. It's okay. So my point is, there are certain differential equations which we can just integrate. But if you have the y prime and the y prime prime as well as a y, the trouble is you can't just integrate it because you have to be able to integrate y prime and y at the same time. But the only way you can integrate the y is if you already know what y is. But that's the question, what is y? What is the solution? So like this technique is limited to very special differential equations. And those are the kinds we mostly solved before in calculus 1 and 2. The ones you can just integrate directly. Another viewpoint here is that every time we did an integral in Calc 2, we solved the differential equation, right? Because, oh come on, where do I have that thing? It's nowhere to be found. Let me write it over here. I probably already said it and just get past it. So my point to you is you've already solved differential equations because every time you solve this problem, right, you have integral of f of x dx is equal to big F, right? Now, I think this is easier to see as a differential equation if I call this thing y, all right? So what you're really saying is dy dx is equal to f of x, right? That's how you judge. Oh, I think I did it wrong. This is hard. This way. Apparently I need to teach calculus again. Let's call this big F. Oh no. The coughing has begun. So suppose that's equal to y. Then this is true only when we have dy dx equals f of x, right? So my point to you was every time we integrate, we're really solving this corresponding differential equation. So this course, one of the things we're trying to do is generally solve differential equations, right? So one way to look at what we're doing, and you can gain a lot of intuition from this, is just to say we're trying to do more integration is another way to look at it. Like solving a differential equation, in some sense or another, is an extension of just integration theory. And that can help you understand why there's constants appearing in the solution, right? So like, if there's just one derivative, even if it's a complicated thing, in some sense or another, it corresponds to doing one integral, right? And when you do one indefinite integral, you get a constant. If you have a second order differential equation, like I just pointed up there, the linear thing, I scroll past now, but well then that's kind of like doing two integrations, right? So you get C1 and C2. And while the techniques we're going to use to solve the differential equation, they're not directly in integration, it's still, in some sense, the source of these constants is kind of like doing multiple integrations. Anyway, so here's some more examples. If I have y prime prime equals to g, I can solve that by integrating once with respect to t, and then again with respect to s, so I get this lovely looking general solution, y of 0 equals y prime of 0 times x, plus the double integral, iterated integral once in s, once in t and once in s, with upper bounds s and x respectively. That's a kind of nice thing. That's a general solution for y prime prime equals to g for any g, provided that the g is continuous. I can do that. I can weaken that even, right? What can you integrate? What functions can you integrate? Certainly continuous functions, piecewise continuous functions. You can do other stuff. But anyway, this is not a course on measure theory. In fact, we will not really do much of careful analysis in here. We don't have the prerequisites. All right, so the initial value problem for an ODE is basically you're given, what's the initial value problem? An initial value problem is you're given a differential equation, something like, differential equation, which is generally speaking some function of nth derivatives, So you're given some differential equation, which you could generally speaking, write as some sort of big old convoluted function equal to 0, right? And then an initial value problem is when you're also given that yn, well, let's say the jth derivative at x naught is equal to y naught. Well, let's say y upper j as an index. These are given constants, right? The point is that you're given conditions, for j equals to 0 all the way to n minus 1. So, for example, if I gave you y prime plus y equals to t, I could have t over there. In this case, the f I'm talking about, we would have f of y prime, y, t equals to, let's see here, it could be y prime plus y minus t. You can always do this, right? The differential equation is some sort of big old function of a bunch of variables. And so an initial value problem would be this differential equation paired with something like you could have y prime of 1 was 2 and y of 1 was 3. The reason this is called an initial value problem is because it's all with respect to one initial value of the independent variable. All right. Now, the theory for solving initial value problems, I'll just give you a view ahead, is very nice. Generally speaking, solutions exist, at least locally. If I have relatively weak conditions on the coefficients of these, I'm going to get a solution. If these are constants, I get a solution which exists for all time, and uniquely so. Once I'm given set of initial values, I need as many as I need 2 for a second order, I need 3 for a third order, I need n for an nth order, I need 1 for a first order. This stands in great contrast to the thing we study at the end of the course, which is the boundary value problem. A boundary value problem is something like this. It could be the same as this, and I could have y of 0 equals to 1, and I could have y of 1 equals to 2. Or I could have derivatives, involving derivatives. But the point is, what makes this a boundary value problem and not an initial value problem is that the independent variables are different. In that case, if it involves different initial and different independent variable values, if that's the data you're given to find the specific solution in the in the class of all possible general solutions, all bets are off. It's much more complicated. There may or may not even be a single solution that satisfies these boundary conditions. Interesting. But I'm just giving you a look way ahead. First, we need to solve initial value problems. And before even that, we need to solve first order differential equations. So let me get this out of my system here. So here's why we care about differential equations in brief. Pretty much everything in physics is a differential equation. This is the thing that struck me as I was an undergraduate major in physics. Every time I got to a new class, there was some new differential equation waiting to greet me there at the most fundamental level. In Newtonian mechanics, you have dp dt equals to the net force. So the primary change of the momentum vector is some given net force. This is a system of ordinary differential equations. And it can be rather nasty. Lagrangian mechanics is based on the total derivative of partial derivatives. This is something called the Lagrangian function. You take partial derivative of the Lagrangian function with respect to y dot, which is the velocity viewed as an independent variable. So, that's Lagrangian mechanics. Again, a differential equation. And that describes a lot of physics. Let me just say that. Electricity and magnetism, the fundamental equations in electricity and magnetism, they're differential equations. They're partial differential equations for the electric and magnetic fields. This is actually a coupled system of differential equations with x, y, z, and t as the independent variables. And again, the 6 field components as the dependent variables, E, X, Y, Z, B, X, Y, Z, the magnetic and electric fields. Now, eventually, when I grow past this course, I'd like to get to understanding this viewpoint, which is that you can state those guys in terms of this. And that's really what's beyond this course. Like, so I just told you, solution is an equation, the solution is a solution is a function, right? Beyond that, there's got to be some deeper way of thinking about these things that doesn't use Cartesian coordinate systems, right? And so that brings us to the world of differential forms and coordinate-free calculus. But that's beyond this course. So I'm just a little comment to add. General relativity also uses calculus on manifolds. Einstein's equation is a differential equation in that context. Quantum mechanics, they said Schrodinger's equation. Schrodinger's equation, again, a differential equation for the wave function. Maybe I have it written here. No, too lazy. And then there's quantum field theory. Quantum field theory, it's got differential equations too. It's all got differential equations. Differential equations is fundamental to all of modern physics, and you need it to really understand things. So with that, I'm going to put this thing away and do some writing. I could rattle off this terminology to you, but it won't entirely sink in until you work some problems and things, of course. That's always, well, I don't know, maybe that's not the case with terminology. Maybe you already understand it. All right, so I've showed you the forest. Now let's try to look at some trees. Well, actually, we're going to look at a particular part of the forest. We're not yet to the point of looking at trees. So this is the first order. Okay, so what is a first order differential equation? So generically speaking, our goal, all right, is to solve something of the form f of y prime yx equals to 0. Now, without much loss of generality, we trade this for dy dx is equal to some function f of x and y. So let's just assume that you can solve for y prime, right? You could think of first order differential equations where it wasn't so easy to solve for y prime, right? I guess I don't have as much to say about those. What would be one where I couldn't solve for y prime? Something that would be clearly in here but very hard to put over there. How about this? Like, e to the y prime. Oh, e to the, well, yeah, why not? E to the y prime, yeah, sure, why not? E to the y prime plus y prime equals to y prime squared. You're like, but you can solve for y prime, right? Well, yeah, I can solve this for y prime. I get y prime equals y prime squared minus e to the y prime. Great. But that's not the equation we're looking for. I have to be able to, let's take as a starting point the somewhat narrow restriction that we can write our differential equation with y prime equals to some function of things that are not y prime. Okay, so this example would it would get in the way of our plan. All right. And we're going to set aside the problem of the initial value problem for a second, for most of what I'm saying. Let's just say that everything I'm going to tell you, I can always give you an initial piece of data, and we can select one solution from our general solution. Okay, so I'll try to say more about that once we're done with our techniques. There are three main techniques, three plans of attack. Okay, there are actually more than that, but three major plans of attack. The one is that dy dx is separable. So So if that's the case, you can separate, you isolate variables, and you integrate both sides. Voila, done. Okay. Well, are you done? That's the question. You're done if you're only looking for an implicit solution. If you're looking for an explicit solution, you might still need to solve for y. The other thing is you have something like dy dx plus p times y is equal to q. If your differential equation looks like that, in other words, if in terms of the terminology I just gave above, if your f looks like q minus py, right? If that's a rather special case, then this is called a linear. This is a linear first order in so-called standard form, perhaps normal form, depending on who you read or whatever. In this case, there is a standard technique. We'll use the integrating factor technique. We can solve any of these. The integrating factor technique, all right? The third, so that's case 1, case 2, case 3. Case 3, we have things so-called exact ODEs. So basically, you can take dy dx equals f and write it as d big F equals to 0. Well, so in other words, and then solution simply big F of xy equals to a constant. So the exact ODEs, they permit solutions which are level curves, like that. Now, it may or may not be the case that your given ODE is an exact ODE, right? Your first order problem may or may not be exact. Putting it in this form, df equals to 0, that's called the Hoffian form. So we'll talk about that. These are the three major cases. There is actually a fourth case, which is often how things are solved in other things like chemistry and whatever else there is. And this is a giant category. There is substitution. So we'll talk about that some. Substitution is when you look at the differential equation and you embed some new variable. Then magic happens, and it usually puts it back into one of these 3 fundamental cases. How many different substitutions are there? I don't know. How much time do you have? There's lots and lots of different kinds of substitutions. But okay. So let's start with separable. So I'll do an example of each of these. So suppose we want to solve dy dx equals to minus x over y. So solve. That's our problem. Now we're going to look at the solution. So it's separable because, well, because what I can do right now. So we think of dx and dy as basically little variables. You're like, well, I was told dy dx is a limiting process. Well, that's great, but this is also true. So y dy is equal to minus x dx. I mean, okay, fine. You'd be like, well, that's just nonsense. Like, you can't write that. The dx and dy are not little real numbers. People differ with you on that opinion. Some people agree, some people disagree. This much is true. This notation I'm using is justified by theorems in advanced calculus with a fair amount of care. So whether or not this technically makes sense, if you really want to think of dx and dy as little real numbers or not, it's somewhat of a moot point because this is at a minimum an efficient notation for implementing well-known theorems in advanced calculus. Okay, so then what do I do? Integrate both sides. By the way, if you wanted to put in an initial condition, you could do that at this point. But I won't do that just yet. So this is 1/2 y squared is equal to minus 1/2 x squared. Now I could add a constant on both sides, but that would be just the same as adding a constant on one side, right? Either way, I could add a constant. Let me just do it. So rather than talking about it, let me just do it. C1 plus C2, right? But I can just as well rewrite this as x squared plus y squared is equal to, gee, what is it? C1 minus C2 times 2. But you know, I'd just rather call this r squared. That seems like a better choice of this constant. Because what are we looking at?
There's a circle.
Yeah, circles. So in fact, you see that the general solution here is this defines, this is an implicit solution of my differential equation, which I'll call star. Now, if I wanted to find a solution which goes through a given data point, right? Suppose I want solution through x naught, y naught. I got really two choices here. One is I can do what I just did. Case one, I could just do what we did. And plug it in. So that would give me x naught squared plus y naught squared equals to r squared. So therefore the specific solution that I have going through that arbitrary point would be x squared plus y squared equals x naught squared plus y naught squared, right? There you go. There's the specific solution through the point x naught, y naught. That wasn't too hard. But there's an alternative method for this kind of thing to find specific solutions through initial data points. Is you could integrate. You could have integrated with this in mind. So I'll show that over here. In other words, instead of making this step, I'll make this step instead. I'll say, well, I could have said integral from y naught to y, and okay. So I feel guilty. I can use a y bar because y is now the particular y we're trying to find at x. And y bar is just a dummy variable integration. You know, I could do like that, and that would give me 1/2 y bar squared evaluated from y naught to y, plus minus 1/2 x bar squared evaluated from x naught to x. And of course, what I get is just the same thing again, right? So it's kind of a moot point whether you want to, I don't really much care if you do it one way or the other, but I would like you to know that you can do it either way. It's also useful for us to just take a second to smell the roses here. What does it graphically look like? What are these solutions doing as we think about the totality of them? I can draw a picture here, right? Solutions are circles. So if you give me any point in the plane, right? Say x naught, y naught, there is a specific and unique solution to this differential equation which goes through that point. Yeah.
So the general solution is all the circles, but like
that is true.
It gives you many possible circles.
Right. It's all possible circles plus this pesky degenerate point right at the origin, right? There's that one zero-dimensional solution.
That's just x
All the
squared
other-
plus y squared.
All the other solutions are one-dimensional. Not in the sense of linear algebra. These are circles.
Okay.
And yet, you know what I mean. We have a sense of dimension from Calc 3. Basically, if something is locally looking like a plane, it's two-dimensional. If it locally looks like a curve, it's one-dimensional. Right? So that's separation of variables. Now, this is my go-to example. I love this example. But one more example, and I will not try to draw the graph on this. What if you have dy dx equals to e to the x plus y? I always get people on this one. See, because in order to solve this, you must first know algebra. So you got to be able to see dy dx is equal to e to the x times e to the y, right? And then you separate. So this gives me e to the minus y dy is equal to e to the x dx. Integrate both sides. You get minus e to the minus y is equal to e to the x plus a constant. And so I could leave it right there. There's my implicit solution. But this one I could actually find an explicit solution for. To find the explicit solution, find an explicit solution that needs what?
Y.
Yeah, that basically means you got to solve for y. So I got to get rid of minus. Now that's a slight abuse of notation. What I've done is I've redefined the constant. So if that bothers you, I'll put a tilde on it. There you go. C tilde, it's minus C. All right. It bothered me. Good. Okay. That's good. And then now I can take the log of both sides, right? So I get minus y is the natural log of C tilde minus e to the x. And so there you go. Y is equal to minus the natural log of C tilde minus e to the x. Of course, you can bring the minus inside if you want. You could also write this as the natural log of 1 over C tilde minus e to the x. As you're working problems out in the book, if you have trouble making contact with the answer in the back of whatever book you're looking, so often, more than not, it's properties of logs that are disguising solutions from what you found. Okay, so there's another example. Let us move on to case 2. So case 2, of course you got to do your homework. This is not enough to understand all that's possible in separation of variables, but it's pretty much it. You already see that the relation between different solutions is not as simple as like we had in Calc 2. In Calculus 2, if I were to graph all of the antiderivatives for a given function, they're just related by vertical shifts, right? So in that case, the solutions to that first order differential equation, they're just like the same shape, shifted up and down. As you can see here, it's not so easy. If I was to solve for y and solve for y again and then add them, I would not again get something that's a solution to the differential equation. So the sum of solutions here, even if you were to explicitly solve for y, would not be a solution, right? Yeah.
You know how we learned in linear algebra about we had quotient like something mod something, and that's what allowed us to like have the sets when you integrate something plus c and let it and that's like
Yeah.
I'm not sure if the terminology, but like is that the same thing with like the solutions here, like when you add constants and stuff?
Well, yeah, I think that's one way to understand it is you're really, in some sense, working with equivalence classes.
Yes.
Yeah. But that doesn't add too much to our analysis, so I'm not going to focus on it. I mean, I think it adds a lot to the understanding of linear algebra. It maybe adds understanding to the general. Students often are like, well, why are there constants? It's like, well, it's because you're not talking about a specific solution. You're talking about the class of all solutions. That's why there's constants there. Okay, so now let us solve. Next up, case 2, linear ODE, first order. So the problem we face is this: dy dx plus py is equal to q. Now here I'm just going to assume that p is, goodness gracious, I think I just need that p is continuous, and this will work. If p is continuous, that definitely means, but even piecewise is probably fine. If p is continuous, though, I can definitely integrate it, all right? So here's the standard thing you do. You say mu is the exponential of the integral of p dx. Or you could call this thing I. I'm going to call it I because that way it looks a lot different than my y. I is easier to see. And I is for integrating factor. But again, some books might use mu or some other letter, or whatever. You're like, well, why do you do that? Well, that's a great question that we can't really answer decently in here. But there are answers from the theory of symmetry of differential equations, but it's a significant investment of time to really understand what I'm saying about that. Anyway, rest assured that this does appear as part of a systematic investigation of differential equations and their symmetries. You can look at the book by Cantwell, for example. He has it in there. Okay, so what is dI dx? So I'm differentiating an exponential. So that we understand, right? The different derivative of the exponential is the exponential again, right? Yeah, then we got to differentiate the inside function. Hey, but that's the derivative of an antiderivative, or a class of antiderivatives. Anyway, the answer is p, right? So we get p times the exponential again. So if you look at that, that's p times I. Right, we get this is d. And we'll look at this. What is this? This is I again, right? So the derivative of the I dx is pi. Well, this is really fantastic because if you go back to the original linear differential equation, which I will now call star, all right, multiply star by I, to get I star. This is usually my notation, guys, something like this. For like, if I want to organize my work, I find this kind of notation useful. Label your differential equation so you can refer to it for one thing. And then if you're doing things, come up with natural labels. For me, a natural label for I from star is I star. And what is I star? Well, I star is I. Let me use a different color here. It is I dy dx. Let's see here, plus IP, or pi if you like, y equals to I cubed. Very smart indeed. All right, so, sorry, it just happened. So this is the thing that always gets students like, but what? What are you doing? What are you doing? Well, that is a good question. I didn't explain to you why I'm doing this. I'm just doing it, right? You can judge it on the merits of what's about to happen, which is that this is ddx of I times p, or excuse me, I times y, right? Because if you do the product rule on this, what's the derivative of the product? Well, it's,
I plus derivative of I plus y.
right. So we write that out. It's di dx times y plus I dy dx, depending on how you write the product rule. The point here is dy dx, well that's, so this is exactly this term, right? And because di dx is what? Pi, the second term is exactly this term. So we can now see that I star is interchangeable with I star tilde A, which will be ddx of Iy is equal to IQ. Because of the reverse product rule. The thing you should appreciate is that this argument I'm giving you is true for any choice of p.
So any continuous function.
Any continuous function, right? And now what do I do? Well, I've got a derivative is equal to another function. This goes back to what I showed you when I had the projector out. You can just integrate both sides. So then it follows that I times y is equal to the integral of IQ, or simply y is equal to 1 over the integrating factor times the integral of IQ dx. And there you go. That is a formula for the general solution. Now, when I have students try to use this general formula, it goes badly for them. Okay, what you really want to do here, the reason I'm going through the proof, in part, is because these steps are the steps you want to do, and you actually want to recreate the proof as you work specific examples. There's a redundancy here, which has like a built-in check of your calculations. I'll show you in an example how this goes. But I think it's important to appreciate this method is general, at least for P continuous. General for linear ODEs. Not every first order ODE is linear. So it's not, understand my general context. Let's see here. So standard example, people like to do something like this. dy dx plus 1 over x, y equals to, oh goodness gracious. I don't know, 1 over x squared, maybe that'll work. Let's see. Okay, so first of all, you gotta recognize. You should recognize that this is a linear ODE. Not terribly surprising given my setup for it. But of course, we don't throw, most people, if they're trying to test you on differential equations, they're not going to say, here's a linear first order ODE, now please solve it. They'll give you a first order differential equation. It's up to you to choose your own adventure, which method you use. All right, so first of all, linear. So I'm gonna try to calculate my integrating factor. It's I is the exponential of the integral of the x over x. By the way, this differential equation has trouble when x is 0, right? So to keep things simple, I'm going to make an extra assumption that x is greater than 0. If x is less than 0, you can still do most of what I'm doing, but you need to put in some absolute values of x's. Okay? Not a big deal. This is the exponential of the natural log of x. I don't need an absolute value because, again, x is positive. Otherwise, I would. Hey, exponential of natural log. Okay, that's just x. Okay. Yeah. So now we multiply. Star by x. Now what was my star? I guess I need to label it. Original differential equation, I'm just going to call star for lack of imagination. I don't know. I'm just making the differential equation famous, right? Yeah.
When you write exponential, you just need like equal something, right?
Indeed. Usual exponential. X dy dx plus y is equal to x over x squared, otherwise known as over x. Now, if I have calculated the integrating factor correctly, at this point we will be able to implement the reverse product rule. If I calculated it wrong, I won't. Now I did it right. So this is the dx of x times y. Right. When you differentiate x times y, you get yourself a y, and you get yourself an x times y dx by implicit differentiation. All of that's equal to 1 over x. Now I integrate both sides. Make sure to add my constant. Here's another place people make mistakes all the time. They don't add the constant until the end. I don't know why. I don't know why they do that. But they do. What's that? We're integrating. Yeah, we're integrating both sides. Exactly as integrating 1 over x. Oh, curses. Thank you. It's always fun when you make fun of people for making a mistake while making a different one of my own. But oftentimes people don't add the constant. You need to add the constant when you integrate. All right. Now you might criticize me. Where's the place I integrate and I did not add a constant? The integrating factor. We'll talk more about that in just a second here, but I'll get back to that, why that didn't matter. I mean, in some sense you could say, well, you found a solution, so it didn't matter, right? That's true, but maybe we should pause and think about our life a bit before we so glibly go on. But there you go, that is the solution, the general solution. I say general, but any of these techniques we're using, we should always be aware of division by zero. Sometimes there's something we're doing, and there's a place it won't make sense because we're dividing by zero. Whatever that is, that may pick up an additional extraneous solution for us. So to really be true to the general solution idea, I should throw that in as a special case or something. It may not fit with my formula, it may. I don't know, depends. So why didn't it matter that I mean, let me just sidebar here in red. Why I can get away with not adding c for the integral of px. So check out what would happen if I did. I would have I is exponential of the integral dx over x, right? So what would that give me? That would give me exponential of the natural log of x plus a constant, right? So that would basically be x times e to the c. So if you think about what happens if I do that, when I go through these steps and I multiply the differential equation by my, let's say, I tilde, well, all that happens is I'm multiplying both sides of the equation by e to the c. That being uninteresting, then I would just divide by it and be back to where we started. So without loss of generality, you don't need to add a constant to the integrating factor. This integrating factor. There is a more general notion of integrating factor where I wouldn't commit to that universal principle. All right. Let me show you an example where there is an extraneous solution. It's kind of fun. So anyway, you can do more of these. I'm just going to give you one example. I have a dozen in my notes. And you guys already saw me count two, so I should move along. As you guys know, I have written missions for differential equations. If you work through my missions, you will understand pretty deeply. All right, so another example, the cautionary, but actually this is a cautionary, but it doesn't, while this is a cautionary tale, it doesn't really make my point for me very well. Let me show you what I mean. This is a very famous one. dy dx equals to y. How do you solve this? Actually, I'm going back to case one for a second here because I realized I need to say something. Separate variables. dy over y equals d dx, right? Integrate both sides. Natural log absolute value of y is equal to x plus a constant. That gives me that the absolute value of y is equal to e to the x plus a constant, which is equal to e to the c times e to the x. So y is equal to plus or minus e to the c times e to the x. Therefore, y is equal to some constant k times e to the x. There you go. That's the general solution. Blah, blah. Population growth, radioactive decay, lots of stuff, right? Well, maybe not radioactive. I mean, I have just the coefficient of 1 here for the growth rate, so it's like, okay, but now that's accurate. If you were to graph the solutions, they look like right? These are the solutions. They look something like this. In the middle, there's this one pesky special case. Case k equals to 0, right? Up here we have k greater than 0. Down here we have k less than 0. If you think about the totality of the solutions together. I would like to point out to you that we have no right. We are absolutely unjustified in including the k equals to 0 case in the separation of variables argument. The thing I forget to say sometimes but I really should because it's kind of important, is that to go from here to here, I assume that y is not equal to 0. Right? So I have to say, okay, y equals 0, I investigate separately. Is y identically equals to 0 a solution? And so you'll see this equals 0. That means that y is the 0 function. All right? Y equals to 0. Well, yeah, I mean, dy dx is equal to 0 in this case, which is equal to y. So, yep, it solves it, right? But we kind of got lucky in some sense in allowing k to be 0. You know? But oftentimes, differential equations are forgiving to those who are analytically ignorant or unaware or whatever. Actually, a lot of math is that way, right? Like that's what we saw in complex so many times. If you just assume complex notation works, like the real turns out to be true. But that's really a victory of good notation as opposed to good thinking. So, with the comment. All right, that brings us to case 3. And then we'll take a break, we'll throw that. And go on to the higher order stuff. I will project an example of the substitutions, but I'm not going to work. Oh man, I got it in my eyes.
Oh.
By the way, something I should mention, these cases are not mutually exclusive, right? There's overlap between these different worlds. That's especially true of what I'm about to do. So this viewpoint of exact ODEs. Well, okay, fine, I'll put the theorem at the start. It's kind of bad form pedagogically, but here's a theorem. Given dy dx equals to f of xy, and I forget, the condition's really weak, like something like partial f partial y is non-zero at some point. So it's something relatively benign. There exists I such that I times dy dx minus f. No, still wrong. Well, let me just use words. Such that I dy dx equals I f is an exact equation. Now this is Pfaff's theorem. I believe Pfaff was a teacher of Gauss. Maybe Gauss stayed at Pfaff's house or something. I hope I don't have this reversed. If Pfaff was a student of Gauss, then it's annoying. Yeah, history. Anyway, Pfaff and Gauss crossed paths. Pfaff is definitely one of the forefathers of differential forms and a lot of what we know and love now in terms of abstract differential equations. But basically this theorem, if you believe it, says we only need case 3. It says you can always find an integrating factor. When you multiply the differential equation by the integrating factor, it makes it exact. You're like, well, why don't we just learn exact? Well, the trouble is finding the integrating factor is actually more difficult than solving the differential equation itself. So it's kind of like, it's an academic comment in some sense, but on the other hand, it is a technique to take a given differential equation, multiply it by something to make it exact. That's something you can do. Now, but I guess I should first tell you what is an exact differential equation, right? I haven't actually told you that yet. So this is out of order in some sense. Sorry, when I got something to say, I gotta say it, otherwise it just gnaws at me. So, here's an example. I'm going to do an example first this time. If I have x dx plus y dy equals to 0, this is said to be a differential equation in Pfaffian form. In fact, this is the differential equation dy dx equals to, let's see here, minus x over y, I believe, in Pfaffian form. So Pfaffian form is when you rewrite the differential equation as a differential equation. Or, to be more specific, an equation involving these differentials, dx and dy. And so basically the underlying idea of the exact equation method is to be able to look at that, tilt your head and squint and say, aha, that is the total differential of some function of two variables. Do you guys remember total differentials from Calc 3?
That first term for you.
Let me remind you, total differential of a function of x and y is big DF, which is partial f partial x dx plus partial f partial y dy. Okay, so with that reminder, can you guys tell me what is this? This is d of what function? Okay, exactly. Now that we've rewritten the differential equation in that notation, it is painstaking. It is obvious what the solution is. How do you have the total differential of something equal to 0 for all x and y? It must, the thing in parentheses must be a constant, right? So therefore, 1/2 x squared plus 1/2 y squared equals to a constant. And then of course we're back to what x squared plus y squared is equal to r squared, because I prefer a constant. I prefer to label my constant in a somewhat suggestive fashion. As you can see, this is the first example we did today. Personally, I find this viewpoint easier than separation of variables when you can see it. Now, the question you should ask is, can you always do this? The answer is no, you can't always do this. So when can you do it, when can't you do it? Let's try to take a slightly more general approach to understand what's going on here. So the generic question is something like generically, or actually generally, but anyway, you might have something like m dx plus n dy. This is the typical nomenclature used here. Use m for the coefficient of x, use n as in n for the coefficient of y. Set that equal to 0, that's your given differential equation in Pfaffian form. The question is that an exact equation? Does there exist some level function such that what? Right, such that this is df, and like you said, you're getting to the heart of it by comparison, right? You see, if that were the case, we need to have these match up, right? We need to have this be partial f partial x, and we need to have n be partial f partial y, right? So that would imply that m is partial f partial x, and n is partial f partial y. So, okay. Now, whenever you have, when you're searching for a criteria and you're trying to see whether something doesn't work or does work, and you get these partial derivatives involved, and the thing you should go to in terms of trying to understand what may or may not be possible, one of the immediate things you should think about is the fact that partial derivatives commute. Partial x, partial y is equal to partial y, partial x, right? So if that's true, we know, what do we know? Partial squared f, partial x, partial y is equal to partial squared f, partial y, partial x, provided that f is nice enough to differentiate. We're assuming that f is a reasonably decent function, so Claude's theorem applies. This is Claude's theorem. So what does that say, though? That says that's the same as saying partial x of partial f partial y is partial y of partial f partial x, unpacking the notation, which is really just to say what, in terms of m and n, the given functions.
Partial n, partial y. And basically partial n, partial y.
Right. I'm writing them in the opposite order because that's the way they're here, but you're right. So this is a necessary condition for the differential equation star. So that is a necessary condition for star to be exact. Is it sufficient? It turns out, yes, that is a sufficient condition with a little bit of, you have to have that condition holds in a simply connected domain. If you have that condition holds in a simply connected domain, we can apply Green's theorem, actually, and argue that, in fact, yes, it is a sufficient condition, in fact, that guarantees that there exists an F. Only in simply connected. If you just have it, it's generally a local result, though. If that holds at a point, if you can find some simply connected, it's that close to the point where that condition is met, and if the partial n partial x equals partial n partial y is true on that whole open set, then you can find a level function f such that the solution to star is just f equals to a constant. How do you find f, though? Suppose you can't just eyeball it like I did in this example. What's the procedure?
You do like the integration with respect to x.
Right. We can integrate m with respect to x, and then we can integrate, and then we can plug that in to the n equation, and then we can solve them successively through substitution is one way. Sure, do that. All right, so let's see here. Sometimes it's helpful to have an example which doesn't work out. So suppose you have y dx minus x squared dy equals to 0. So here we have m, here we have n with a minus, right? And you can see that partial m, partial y is equal to 1, and partial n, partial x is minus 2x. So we can anticipate that is not an exact differential equation. I cannot use the technique of exact differential equations to solve it. Now, if I try to go through the iterative procedure that Daniel was just talking about, so I suppose partial f partial x is equal to y, and I suppose that partial f, we know this is crazy, we know it's not going to work, but let's just see what happens when we try to make it work. It's instructive. So partial f partial x equals to y, partial f partial y equals minus x squared. When we integrate the first differential equation with respect to x with y constant, this gives us f of xy is 1/2 y squared plus c1, which is in principle a function of y, because we're holding y as a constant as I do that integration, right?
Or integrating with respect to x.
Oh, yeah, my integration's wrong. Sorry. Thank you. Yeah. Oh well. Eventually I'll learn. So xy. Right. Now we agree. Now if I take that, right, and I plug that down into here, I get partial y of xy plus c1 is equal to minus x squared. But differentiating this gives me x plus, well, it's really dc1 dy because y is only a function, c1 is only a function of y, It's a partial derivative of C1 with respect to y. In fact, an ordinary derivative of C1 with respect to y. And that's equal to minus x squared, right? So what you get is you get dc1 dy is equal to minus x squared minus x, which is impossible. Unless C1 is just a constant. No, that's still not possible. It's just not possible. So this is a contradiction. So you see, no such f exists. This equation is inexact. Of course, we didn't need to do all that work because we went through the general discussion over here, and we know we can use that simple do the derivatives match test to see whether or not it's exact from the test. It's probably worth looking at Green's theorem for just a second here before I go on. Do you guys remember Green's theorem? So suppose we had simply connected domain S, simply connected. And suppose we looked at the integral around the boundary of S, consistently oriented. Let's see here. So that would be like this direction. I'm assuming that the normal to S comes out of the board. All right. Green's theorem says that closed integral around the boundary of m dx plus n dy is the double integral over S of what? Well, it's partial n, partial x, minus m partial y, right? So, if m and n exist, right, on an open set a little bit bigger, let's say, than S, right? So if they exist on the edge, on the boundary of S, well then, if they exist over the whole boundary, that should be 0. Right, I think. Or should that be 0? Oh, excuse me, that shouldn't be 0 in general. What? So if this, actually there's no reason for this to be 0 around the boundary in general, because you can integrate a vector field around the boundary of some simply connected set and get non-zero, right? In the case the vector field is not conservative.
We're assuming it's 0.
Right, we are, well, we're assuming if this is an exact equation, you see what happens, this is the gradient of f. See, because the gradient of f is partial n partial x, partial s partial y. So in the case that was an exact differential equation, that line integral is the integral of the gradient of a level function. And the integral of a gradient around a closed curve is 0. Right? You pick any point. This should be, f of p minus f of p. So my fundamental number calculus for line integrals is 0. So what you see then, guys, is because that has to be 0, and because Green's theorem holds for simply connected, then, well, look, we can work it the other way around, right? If this is 0 for arbitrary such s, that gives you that the integral around the boundaries of these arbitrary simply connected little subregions is 0, which shows you that this m comma n is a conservative vector field on any little subregion. But then that implies that there exists a potential function for it. And consequently, the original differential equation is exact. There's a connection between these ideas. On the flip side, of course, if these are not equal, even on some little open set, then this gives you a non-zero thing. At least if you select the subset, which is say positive or something, or whatever. And if that's non-zero, that means that this isn't conservative, which means that there doesn't exist a potential energy function out such that you can gradient to get back to vector field. I don't often emphasize these ideas too much in differential equations because talking to most students about potential energy and conservative vector fields, I'm just talking to them about the part of calculus 3 that they don't really understand. So it's kind of like just rubbing salt in the wounds. I'm introducing something new and I'm then using something that they don't understand to confuse them more. But it is true to really understand this. You should understand this connection with Green's theorem.
So there is some connection between the conservative vector field
Yeah, a conservative,
and it being able to be exact.
right, in fact, I mean, the connection is this. F, two-dimensionally, Mn is conservative on S subset of R2. If and only if n dx plus n dy equals to 0 is an exact equation on S. That's what I just explained. Okay. Okay, so finally, let's look at a couple examples of the projector and then we'll take a break. Think back. You can do it. You can do it. You can do it. Come on. We're waiting. Thanks. So of course, I have some of this stuff I'm showing you. Whoa. Here's a good one. With the walking on the ceiling, and I guess they're always walking on the ceiling. There we go. Now I can see it better. So, here we have 2x y squared plus 10th dx plus 2x squared y minus sine of y dy. This is already in Faffian form, right? And so I guess my point here is just I can look at that and write the level function down. I mean, I can go through this two-step integration process, but if the problem's simple enough, if you can guess what f total differentiates to the differential equation, why bother going through this procedure? You know, if you can find the function that differentiates to the solution just by looking at it, then do so. That's our goal, is to find the solution, right? And here it's not hard to check that it in fact works, because partial f partial x is 2x squared y, and partial f partial y is that. So there you go, that's this. And the solution to the differential equation is x squared y squared plus cosine y equals to k. I a lot of times have students just box in the formula for the solution, but that shows to me that they don't really understand what's going on. F is not itself the solution. F equals to a constant. The solution set, the locus to the solution, F equals to a constant. The points which solve that equation are actually the solution to the differential equation. F is merely a tool to construct that solution. So we should understand that. See if I can find one here where I don't. No, again, I'm just guessing. I should have an example in here somewhere where I actually worked through it. Was that up here? Did I just skip through? Yeah, it is. Okay, duh. My first one I actually worked through. So here I had y squared dx plus 2x y dy. I have partial x equals y squared, partial y is 2xy. Integrate this one with respect to x, I get x y squared plus some constant of y, right? Then what I'm going to do is I'm going to take this template of the solution for f, and I'm going to plug it into there, right? But unlike the one I just covered up, this one's going to work, because when I partially differentiate with respect to y, this gives me 2xy, which is balanced out by that term. Let's see how that goes. Yes, partial f partial y is 2xy, which is equal to f of x. So that shows you that. Oh man, what did I do? Did I not write it down? Oh. anyway, the solution then is just xy squared for f. Again, that's not the solution. The solution for f, but not the solution for the equation itself. The differential equation has solutions xy squared equals to k. And if you want to think about that in terms of an explicit solution, it depends on what point you're thinking about. There are actually 4 different cases you got to think about. By positive, by negative, and that's going to give you basically y is plus or minus the square root of k over x, and that's going to either be quadrant 1, 2, 3, or 4, depending on the choice of plus or minus, and depending on whether k is positive or negative, where that graph actually is going to be found, right? Yes, sir?
So the points that, I guess, like fit the function or the like coordinates that, or the points that are the solution, basically.
Yes.
Okay. The different equations, so.
Right, right. This is a cute formula I found in Richter and Rose. So for the this is actually, suppose you want to solve an exact equation and you want the solution to go through the point x naught, y naught. You can do this particular integration. You can integrate from y naught to y, the n function with x naught stuck in, t variable, and then integrate from x naught to x, the m function with t put here and y like that. You notice there's an asymmetry in this formula. That's all explained here in terms of just doing a line integral. I'll let you read it, but it's really a cute formula because this automatically builds the initial data point into the equation. And if your solution to the exact equation is rather complicated, this is cool because it builds the initial point into the formula directly. It's a nice technique. You won't find it in all books. I found it in Richter and Rose's classic, which you can get from Amazon for about $5 now. Awesome. Let's see here. Do I actually? Maybe I. Here's that technique put into practice. Our go-to example. 2x dx plus 2y dy. So I follow the rule, which is to integrate that and that, and now this pops out directly. Now that's not too impressive because that was pretty easy to fit the initial condition to anyway. My point is for more complicated, one it would also work. All right. About that, I want to show you a couple pictures and we'll stop. You can investigate when is it possible to find a integrating factor. If you think about that, basically what you want to do is multiply your differential equation Faffian form by I, and then the new coefficients, im and in, you're going to want those to satisfy the partial y of the x1 to be equal to the partial x of the y1. And so that will give you conditions then on I, which will make it an integrating factor or not. And that's what this is about. There's usually a couple. I don't know if I had these in my notes. Oh yeah, here, well. So here's a kind of problem I have in the mission. Basically, you got this differential equation, and the question is how to make it exact. I give you this ansatz, this guess, that if you multiply that by x to the a times y to the b, for correct choices of a and b, you can make it exact, right? So you multiply it, and then you force the necessary condition to be satisfied with the right choice of A and B. It's ugly, but here's your n, here's your y, differentiate that with respect to y, differentiate that with respect to x, you get this lovely equation. It forces you to choose A equals to 1 and B equals to 1. Then you go back to your original differential equation, you multiply by x, y, it makes this inexact equation become exact. Bammo, you can solve it. It's kind of a standard problem. You can also prove that the linear first order differential equation, the one we solved with the integrating factor technique, when you put it into its Faffian form and you multiply by the integrating factor, you can prove that in fact that is an integrating factor in the same sense I'm talking about it with exact equations. Here's the proof of that. I start with dy dx plus py equal to q. I rewrite it in Faffian form, which is this. And that's not exact because here n is that, right? So partial n, partial x would be 0. Partial m, partial y would be p. Of course, p is not generally 0. If p is 0, then it's separable. So it's also exact in a kind of stupid way. And so the integrating factor I, what you need is that I times this plus that is exact, right? That means partial y of this equals partial x of that. And so if you make a relatively benign assumption that I is only a function of x, I believe, that leads you to this, that IP is equal to di dx. In other words, so if I is only a function of x, that becomes di dx, right? This becomes, if I is only a function of x, then the only thing with a y dependence is just that y, so this becomes IP. You got IP is equal to di dx. Separate variables, integrate, you get integrated factors, the exponential integral of pdx. So I told you earlier today, you can't really explain where the integrated factor is coming from without highfalutin symmetry methods. It's not entirely true, this kind of shows you. But my feeling is that this still lacks some naturalness, like this argument. I mean, there's an argument in the symmetry of differential equations, which is, to me, more profound, but whatever. Integrated factors are not unique. Well, anyway, I'll let you guys, you really should read my notes to get the full flavor. I'm not going to do everything in here. I just want to show you a substitution or two. Here's a pretty standard one. I have dy dx equals to v over x plus 1 over y over x minus 1. So you kind of see, well, I've got this y over x term, right? So a natural thing to make a substitution for is v equals y over x. Now when you do that, you got to be careful because that tells you things like y is equal to xv. So when you differentiate, you get dy dx is v plus x dv dx. And so you got to put that in whenever you got a y prime. And then you do that, do some algebra. Hey, rational function, we own these, integrationally speaking. And so then it basically makes, making that substitution makes the problem separable. Ugly? Yes. Separable? Also true. There's a solution. So generically speaking, if you can see your differential equation in terms of y over x, you make the substitution v equals y over x. Good stuff happens. That's one problem. Another class of problems is the Bernoulli equations. The Bernoulli equations are differential equations of a very specific form, but kind of pseudo-linear. They're like almost linear, but there's a y to the n over here. So it turns out you make the substitution, well, you multiply by y to the minus n first, all right? And that brings you to this. And then you make a substitution, z equals y to the minus n plus 1, and that changes it to look like this, in which case it becomes, making that substitution converts it into a linear ODE in the new variables, which then you can solve by the integrating factor technique. Bernoulli equations, slightly nastier. Here's an example of one. Oh no, maybe I don't even have an example of one. Do I have an example of one? I don't know. There's another, that's one thing you do. So you can study these Bernoulli equations, sure I have some of the homework. Another technique of substitution, which I'm fond of, is just total coordinate change. So not, the ones I just talked about, we changed like the dependent variable or the derivative. Here I'm suggesting something else. You could change both the dependent and the independent variable. That's a deeper technique of substitution. That's really simple in Pfaffian notation. Basically, if I have, for example, if I'm changing the polar coordinates, at x equals to r cosine theta, I've got y equals to r sine theta. So what's dx? Well, dx is nothing more than cosine theta dr minus r sine theta d theta. And dy is r sine theta, right? So that's sine theta dr plus r cosine theta d theta. Just take the total differential of the polar coordinate equations. That shows you how to change the dx and dy. And then, of course, the x and y we already know how to change into polar coordinates from just our basic, experience with polar coordinates in calculus 2 or 3 or whatever. For example, here's one. This differential equation is pretty nasty, right? But if I can make dx this, I can make dy that. I'm just taking the total differential of the polar coordinate equations again. This is r, right? So this is actually cosine theta, right? This is r squared sine squared theta. This is sine theta, that's minus r squared sine theta cosine theta. And so you get this, which may or may not be helpful. I don't know. Which gives you that, which separates, and there's a solution. Now, I will warn you, this is a treacherous business. I have tried to create examples before and have them blow up in my face. I could not give you a general instruction as to when this is going to be successful or not. That's the thing about substitutions, is I can't really tell you, oh, it's always going to work if blah. Not, well, I know that's true for integrating factor technique and a couple of special things, right? But generic, when do substitutions, when they work, when they don't, it's a mess. Here's an actual Bernoulli equation problem. Oh, no, it's not. It's something like a Bernoulli. I don't know what this is. Oh, this is just reduction of order, which in some sense doesn't belong here. But I don't know where else to put it. So reduction of order is when you can make a substitution like v equals y prime. It changes to second order problem, become a first order problem. You can solve the first order problem, then you can go back and solve the second order problem. So the reason I say it doesn't belong is I'm technically solving second order differential equations using first order technique. Finally then, I told you I want to show you pictures. I don't have too much to say about applications. I have got lots of applications in here you can look at. It's fun to think about geometry of differential equations. For example, this one, I have the differential equation. Well, I said find a family of curves which are increasing whenever y is less than minus 2, or y is greater than 2, and they're decreasing whenever y is between minus 2 and 2. I mean, how would you find a system of curves like that? I say the natural thing to do is to look at a differential equation that has y plus 2 and y minus 2, right? This, if you think about it, it's going to be, I believe it's going to be negative. No, it's going to be positive. Well, this would be what? If y is greater than 2, positive. If y is less than minus 2, it's positive again, right? Is that right? Yeah. So if I multiply that by minus, then that gives me what I want, I think. Do I have that right? Did I read it backwards? Sorry. Oh, it's already what I want. So anyway, the point is if I could read my own writing. This differential equation fits the bill of having dy dx being either positive or negative where I want it to be increasing or decreasing. And then I can solve that differential equation to find the curves. Separate partial fractions. You get this stuff done here. But it's instructive to actually just look at the differential equation directly with something called the direction field. And that's where MATLAB's p-plane function is a fantastic tool. This is in MATLAB, it's called the p-plane. There's Java output for it. If you don't have MATLAB, it's not a big deal. You can find it. And what you have plotted here, actually, I forget, maybe I have it turned off right now, but these places, these little circles are just places I've clicked. And wherever I've clicked, it's plotted a sample solution. So this is a numerical tool. Basically, it sets up this graph, and then you click on points. It creates the solution, not through solving the differential equation directly, but by using a numerical technique to graph the plot and then graph the solution. And then you can see it as, increasing, decreasing. Oh, it's bothersome because it's opposite of what it said.
I mean, it's like you put it in the problem.
Yeah. Y plus 2, y minus 2.
It's positive, minus greater than 2.
Uh-oh. Just a second, I gotta take this guy. Hello? Good? Oh my goodness, I will go, I'll be right in there in just a second. Thanks. Okay, bye. Oh, man, I forgot something. Can you stop that for now?
Yeah, sure.
We'll just take it up in a minute.